linear algebra. Lecture 4. And what we were studying were systems of linear equations. And writing the solution space as an affine space. And someone had asked me to do a problem involving, actually, I think it wasn't even a system of linear equations. It was just one linear equation, inhomogeneous, in 3 variables. So, and I don't remember which one I was asked to do. So if you're here and you want to tell me a particular problem.
Professor, it was question 4.
Question 4 on which page?
Page 21.
Okay, just a second.
Wait, was it 4? Let me see.
3x minus 2y minus z equals 0 and equals 5. Is that the one?
Wait, I'm not sure. Let's see.
And
Oh, it was 8. No, it wasn't 8.
Sorry, which one?
It was 7x minus 3y plus 2z.
So there's a problem number 2, 7x minus 3y plus 2z equals 6.
Yes, it was that one, yeah.
Okay. So let me just solve the equation and write the solution as an affine space. And then I'll go back and check the particular solutions. So this is on page 21, number 2. We have the equation 7x minus 3y plus 2z equals 6. So there are many, many, many different ways that we could solve the equation. The simplest is you solve for one variable in terms of the others. So let's say we solve for z. In terms of x and y. So 2z, you bring everything else to the right-hand side of the equation, is 6 minus 7x plus 3y. So again, you have to check my arithmetic because everybody makes mistakes and you have to find the mistake and correct it if you made a mistake. Divide by 2, you get 6 over 2 is 3 minus 7 halves x plus 3 halves y. So a solution of this equation, x, y, z, for any x and y, they can be chosen arbitrarily, but then z has to be equal to 3 minus 7 halves x plus 3 halves y, which I can write as if I like as the sum of the vectors, and this is not, you certainly don't need to do this, but I could write this as like with the x here and the y here. This is x, y, and this, but and you can see they're sort of lined up in columns. This is 0, 0, 3. This is x0 minus 7 halves x. And this is 0, y, 3 halves y. And so I could, if I like, just write this. I could factor an x out of this vector. This is 0, 0, 3 plus x times the vector 1, 0, minus 7 halves plus y times the vector 0, 1, 3 halves. So this is one form in which I could write an arbitrary solution of this inhomogeneous equation, or I could also write it like this if I choose, and just to avoid fractions. I could factor a half out of this. This would be x over 2 times the vector 2, 0, minus 7. Because again, if I do scalar multiplication of this vector by x over 2, I get x times the vector 1, 0, minus 7 halves. And if I factor a 2 out of this, this would be let's check that I didn't make a mistake somewhere along the way. Yes, this is.
I have a question.
Yeah, go
Shouldn't
ahead.
x be 1?
Sorry. What I didn't hear what you had. I didn't hear your question.
So my question was, I want to understand where it says z equals 3 minus 7 over 2, 1x. How did you get that?
So I have this equation.
Okay.
If I bring 7x minus 3y to the other side, I get 2z is 6 minus 7x plus 3y. Right? Do you see where this comes from?
Yes.
And then I divide by 2.
Oh, okay.
So then this is xy, and z is z minus 7 halves x plus 3 halves y. And this is 0, 0, 3, x0 minus 7 halves x, 0, y, 3 halves y. And
Yeah, I understand. Thank you.
and or I could write this as, if I think of 1 as 2 over 2, I could factor out a half. I would get x over 2 times 2, 0 minus 7. I think of this as 2 over 2, and I factor out a 2. I get y over 2 times the vector 0, 2, 3. For any x and y. And if x and y can be anything, the same is true for x over 2 and y over 2. So let me just write this over here. The solution space of the equation 7x minus 3y plus 2z equals 6 is the affine subspace, that's called L, which is all vectors of the form 0, 0, 3 plus x times 2, 0 minus 7 plus y times 0, 2, 3, where x and y are all possible real numbers, all possible scalars. So this is the solution space of this equation. Now,
Question?
yeah, just 1 second. Yes, go ahead.
Yes. How did you get the solution space 0, 0, 3 to 0, negative 7?
So my solution space x, so for any x and y, z must be equal to this linear function of x and y. So every vector x, y, z that's a solution, x is x, y is y, but z is equal to this. And then I'm writing this vector as a linear combination of three vectors. I'm decomposing this. If I take the vector 0, 0, 3 plus the vector x0 minus 7 halves x plus the vector 0, y, 3 halves x, if I add these three vectors together, I get this. This is just vector addition.
Okay.
And I do that because now I can factor an x out of this. So I have 0, 0, 3. I have x times the vector 1, 0 minus 7 halves. Right? This is 1. And I have y times the vector 0, 1, 3 halves. So every solution of the linear equation is of this form. But if I want to avoid fractions, I could leave it like this. This is 100% correct. But the form in which it was given in the problem, I factored out a half from this vector. So I got x over 2. Instead of x times this, that's the same as x over 2 times 2, 0 minus 7. And this factor is exactly the same as y over 2 times 0, 2, 3. And x over 2 and y over 2, again, these are any real numbers. So this is just a linear combination of these two vectors plus this. So that's how I get my solution space. And for this equation, you can check, for example, that if you take the vector 5, 9, minus 1 and plug it into this equation, what do you get? 7 times 5 minus 3 times 9 plus 2 times minus 1. That's 35 minus 27 minus 2. That's equal to 6. So this vector is the solution of this equation. By that x equal 5, y equals 9, z equal minus 1, I get a solution. So this vector is in the solution space, which means this vector, 5, 9 minus 1, can be written in the form 0, 0, 3 plus x times 2, 0 minus 7 plus y times 0, 2, 3. So I want to find x and y. I want to be able to write this vector as as a linear combination that looks like this.
I have a question.
Yes.
So you see in the solution space where it says L is equal to, and then you continued on to writing, so you gave us like the optional kind of solution, and where it says 0,
Well, I'm not
0,
sure what
3
you mean.
plus.
What do you mean by optional solution?
So like you said, we can either do it like one way or kind of factor out the fractions to make it simpler.
Correct.
So that way, so you see where it says like 0, 0, 3 plus x, but you didn't put the over 2 there. Is that supposed to be there, or is it not
No,
supposed to be?
because if x is arbitrary, so is x over 2. Every number is of the form x over 2, like 10 is the same as 20 over 2.
Got it. Okay. Thank you.
So let's see, but I want to compute the x and the y that represents this vector as this kind of linear combination. So I want to find x and y that solve this vector equation. What does this equation say? If I add these vectors, this is 2x, 2y, 3 minus 7x plus 3y. I want to find x and y such that this is equal to 5, 9 minus 1. So for this to be the case, it must be that 2x equals 5. So x is 5 halves. 2y equals 9. So y is 9 halves. And 3 minus 7x plus 3y, what is that? That's 3 minus 7 times 5 halves plus 3 times 9 halves. That's 3 minus 35 over 2 plus 27 over 2. This is minus 8 over 2, or minus 4, which is minus 1. So I'm done. So
I have a question.
so x equal 5 halves and y equal 9 halves are the scalars that give us a representation of the vector 5, 9, minus 1. Yeah, go ahead.
Where did you get 5, 9, and negative 1 on the left-hand side?
So in the original problem, if you look in the book, problem 2, part A, gives 4 particular solutions of the equation. So this is just given. And one of those 4 is 5, 9, minus 1.
Okay.
Okay? So this, and I checked, this is a particular solution of the equation. This is the general solution. That means that every solution can be written in this form. So part C of the problem is to represent each particular solution in this form. So I'm looking at this one solution, 5, 9, minus 1, and I'm finding the x and y such that 5, 9, minus 1 is of this form. So 5, 9, minus 1 is one of the particular solutions that's given in the statement of the problem.
Do we have to prove all of them, or just we can just choose one, like we did 5, 9,
Well,
9?
the assignment was to prove them all, but it's just to give you practice. But the method is the same. So if you do one correctly, you can certainly do the others correctly. When I grade the homework, I don't look to make sure you've done every single part of every single problem. I just check to make sure you've done a reasonable selection of the problems. Obviously, if you do them all, that's great, but you can still get, full credit for the homework if you've done most of the problems. If you do one problem out of 10, you don't get the full 2 points.
And does every problem have to be correct to get
No,
2
no,
points?
You have to work on the problem, and I don't grade individual problems. If you have a question about whether something is correct or incorrect, you should ask me in one of the problem sessions, one of the office hours, when I'm just there to answer questions of that sort.
Okay.
Any other questions about homework? So let's continue then. So we're looking at systems of linear equations, and the general method, the most important general method to solve them is something called Gaussian elimination. And let's talk about that. So just as in the case of a system of linear equations, you might have m equations in n variables. So the standard way to write a system like this is the first equation is a11x1, a12x2. Then you come to the jth variable a1jxj up to a1 and xn equals b1. So this is one equation in n variables. The right-hand side could be 0 or could be non-zero, but we're not specifying what b1 is. This is our first equation. And the second equation, we use double subscripts for the coefficients. The first subscript indicates the number of the equation. The second subscript indicates the variable. So for the second equation, first variable will be a21x1, a22x2. For the jth variable in the second equation, it would be a2jxj up to a2nxn equals b2. When we get to the ith equation, I is between 1 and m. They're m equations. The ith equation will be ai1x1, ai2x2, aijxj up to ainxn equals b sub I. And finally, we get to the last equation, which is equation number m. That's am1x1, am2x2, plus amjxj up to amnxn equals b sub n. So this is a system of m equations and n variables. And the labeling of the subscripts is standard, it's important, and you have to always get it right. If you're looking at the ith equation, and in that equation, the jth variable, the coefficient is always written as aij. I is the equation number, j is the variable number. So this never changes. The equation is the system is homogeneous if all of the b sub I equals 0, the right-hand sides are all 0 for all I, and inhomogeneous if even one of these is non-zero, if b sub I is different from 0 for some I. So in a homogeneous system, all the right-hand sides are 0. In an inhomogeneous system, some of the right-hand sides may be 0, but at least one must be non-zero. And for the homogeneous system, the solution space is a subspace of Rn. Right? The solutions are column vectors in Rn. And for an inhomogeneous system, the solution space is an affine subspace. Translate a shift of a vector subspace, just as in the one equation case. So let's solve an equation. Oh, sorry, let's solve a system of equations. In the text, I write out in great detail exactly how one uses Gaussian elimination, but the simplest way to understand it is just to see how particular examples are worked out. The idea in Gaussian elimination is if you have a system of equations, there are certain operations you can do to the system that give you a new system, but with exactly the same solutions. And the idea is to choose the operations on the system that simplify the system. So you end up with an equivalent system that's easier to solve. And what are the operations on a system of equations that give an equivalent system? So again, I'm sorry that my handwriting is so bad, but that's one reason why I spent a lot of time writing out a text, printing it out in book form. So the simplest operation is you can interchange two equations. So if you have the same equations in a different order, changing the order of the equations doesn't change the solutions of the system. So you can interchange two equations. You can also multiply an equation by any non-zero scalar. This just means if you have the equation 3x minus 4y equals 7, that's exactly the same, that has the same solutions as the equation just multiplied by 2, 6x minus 8y equals 14. These two equations have the same solutions. I got from here to here by multiplying by 2.
What does one say?
Interchange two equations.
Interchanged. Okay.
And the third operation is to add a multiple of one equation to a different equation, to another equation. So let's look at an example. I'll start with some of the examples in the book so you can follow it live, or you can follow it even when you study it at home. So this is on page 34. We have the system of equations 9x plus 11y equals -1. 5x plus 6y equals 3. So it's sometimes easier to deal with an equation with the leading if the coefficient of x is 1. So I could take this first equation and multiply it by 1/9, that is, divide by 9. I would get x plus 11 over 9y equals -1/9. And I don't touch the second equation, 5x plus 6y equals 3. So how did I get from this system of two equations to this system? I didn't touch the second equation, but the first equation I multiplied by 1/9, and I got this. Okay.
I have a question.
Yes.
At the end of number 2, what word is that? It says by a new scalar?
Non-zero scalar.
Non-zero? Okay.
So here I multiplied this equation by the non-zero scalar 1/9. I multiplied this equation by 1/9, and this is what I got.
And at number 3 at the end, it says multiply of one equation.
Add a multiple
Add a
of
multiple.
one equation to another. Let me give an example of what that means. Here I have these two equations. The first equation is x plus 11 over 9y equals -9. Let me add a multiple of the first equation to the second. And what multiple am I going to pick? -5. So I'm going to multiply this equation by -5 and add it to this. So I have -5x plus 5x is 0x. That's actually why I did it. Yeah. Let me just, over here, put it in a box. So I take the equation 5x plus 6y equals 3. Take this equation, multiply it by -5. I get -5x minus 55 over 9y equals 5 over 9. Right? If I multiply this equation by -5, I get this. And then I'm adding -5 times the first equation to the second. When I add, I get 0 times x. 6 minus 55 over 9 is -1 over 9y. And 3 minus 5/9. 3 is 27 over 9. 27 over minus, sorry, I'm adding. 27 over 9 plus 5 over 9 is 32 over 9. So when I add -5 times this equation to the second, I get just -1/9 y plus equals 32 over 9.
How did you get 32 over 9?
What?
At the end were 3 and over 5/9. How did you get 32?
3 plus 5/9. 3 plus 5/9 is 27/9 plus 5/9 is 32 over 9.
Okay.
And how about the 1 over 9?
Which 1 over 9? Here.
No, the bottom part. You did 6y minus 55 over 9.
Well, so you have to know fractions. What is 6 minus 55 over 9? 6 is the same as 54 over 9. Minus 55 over 9 is -1 over 9.
Oh.
Right? I mean, you have to be able to do arithmetic with fractions. When you're doing a homework, you can always use a computer calculator, but not during an exam. All right, so now I have this. So let me look. I won't change the first equation yet. The first equation is x plus 11 over 9y equals -1 over 9. But let me multiply the second equation by -9. So I'm allowed to multiply an equation by a non-zero number. I multiply by -9, I get y equals -32. Well, so that's what, so this equation, y equals -32, and then me add, if I just plug -32 into this, I can solve for x, or what is the same thing, y equals -32. If I take -11/9 times the second equation and add it to the first, I get x plus 0 equals -1/9 minus 11. Sorry. I get minus 11/9 times this, minus 11/9 times 32. What is this? 11 times 32 is 352, plus 1 is 353. Is that right? Yeah. So I get x equals minus, no, let me do it, sort of squeeze it. So here, x, y is -32. So x is minus 11/9 times 32 minus 1/9. So this is minus 353 minus 1 minus 354/9. Somehow my arithmetic isn't working out properly.
Shouldn't it be -32?
Oh, thank you. Okay, yes. Negative. So this is plus 352. No. So this is 352 minus 1, 351/9. And 351/9 is exactly 39. So what my calculation has done is the following. I have the system 9x plus 11y equals -1, 5x plus 6y equals 3, and I claim the solution is xy equals 39 minus 32. So let me check. 9x plus 11y is 9 times 39 plus 11 times minus 32. Let's see. 9 times 39 is 351. And 11 times 32 is 352, and the difference is -1. So that checks. And 5x plus 6y is 5 times 39 plus 6 times minus 32. 5 times 39 is 195, I think. Minus 6 times 32 is 192. Is that right? Something's wrong. 5 nines are 40. Yeah, 195 minus 192 is 3. So that also checks. So everything is good in the world and everything works out okay. So let's look at a more complicated system. So this system of equations, the solution space consists of just one vector. So solution space L is just the vector 39 minus 32, which is a affine subspace. It's this vector plus 0. That's the solution space. Let's look at the next system. This is example 2. Maybe I should start on a good piece of paper because these problems take a lot of work. Oh, before I do that, this was my system of equations. Let me see if I can share the screen with a Maple worksheet. So there's a simple command in Maple to solve an equation or a system of equations. It's very simple. It's just say solve. And if you have an easy equation like 3 times x equals 27, comma x, that means solve for x. When you multiply in Maple, should put in a multiplication sign. This is, sorry, 3 times x equals 27. Well, the solution is x equal 9. Right? That's pretty easy. When you have a system of equations, the syntax is a little more complicated. It still is solved, but if you have more than one equation, you put them in curly brackets. So in the problem we just looked at, it was 9 times x plus 11 times y equals minus 1. And 5 times x plus 6 times y equals 3. So those are my two equations that I want to solve, comma, and then the variables are x and y, and I put them in curly brackets as well, and then a parenthesis, semicolon. Aha. So here we go. Didn't have to do any work. Maple gave us exactly the solution that we found by hand. Very nice. It's just interesting to use Maple to check out and it works sometimes. So let me look at example 2. What happened to it? Yeah. So this is example 2. This is on page 34. So we have 2 equations and 3 variables.
Professor,
2x plus,
example 1, you said it was on page 39.
no, 34. Sorry, example 1, it was also on page 34.
Okay.
2x plus 3y plus z equals 1. 5x plus y minus 4z equals minus 1. So I can use the 3 operations that I'm allowed with Gaussian elimination. I can multiply an equation by a non-zero scalar. I can interchange equations, and I can add a multiple of one equation to another. So let me start. I want to get this coefficient of x to be a 1, so I'm just going to multiply the first equation by a half. If I multiply a half, I get x plus 3 halves y plus 1 half z equals a half, and I don't touch the second equation. Okay. And again, at each step, if there's a question, you have to stop and ask it and interrupt and ask how I did it, because if you miss a step and you go forward, none of it makes any sense. All right, so now I have my first equation, x plus 3/2 y plus 1/2 z equals 1/2. And I want to eliminate x from the second equation. So I can subtract 5 times the first equation from the second. So if I subtract 5 times x from 5x, I get 0 times x. Here I get y minus 5 times 3/2 x. That's, let me do this in sort of painful detail. 1 minus 15/2 y. Right? It's y minus 15/2 y. And then it's minus 4 minus 5/2 z equals, it's minus 5 times this is 1 minus 5/2. So this is exactly the same as x plus 3/2 y plus 1/2 z equals 1/2. This is the x's disappear in the second equation. This is minus 13/2 y minus 4 minus 5/2 is minus 13/2 z equals 1 minus 5/2 is minus 3/2.
I'm sorry, for the first part, why is it minus 13/2 y? Can you explain that?
Yeah. 1 minus 15/2 is 13/2.
Okay, got it. Thanks.
Sorry. And here this is minus 5/2 minus 1 minus 1 minus 5/2, which is minus 7/2. So if I subtract 5 times the first equation from the second, the x disappears, and this is what I get.
I have a question.
Yeah.
How did you get the second row of subtracting 0 x from 5x, the second row?
So here I have this equation. 5x plus y minus 4z equals minus 1. Okay?
Okay.
Now, if I take the first equation and I multiply it by 5, I get 5x plus 15/2 y plus 5/2 z equals 5/2, right? And if I subtract this from this, these cancel. I get minus 13/2 y minus 4 minus 5 is minus 13/2 z minus 1 minus 5/2 is minus 7/2. Right, so that's how I got this second equation. And I eliminated the x. This is why it's called Gaussian elimination. And then I want to get this y to have a coefficient of 1. So I'm not going to change now the first equation. This is still x plus 3/2 y plus 1/2 z equals 1/2. But I'm going to multiply the second equation by minus 2/13. And that gives me y plus z equals 7/13. So this is already looking simpler, and I eliminated the x from the first equation. But now I can eliminate the y from, I eliminated the x from the second equation. I can eliminate y from the first equation. I simply, see, my second equation is y plus z equals 7/13. If I take the first equation and I subtract 3/2 times the second, so I get x, 3/2 y minus 3/2 y is 0 y. And 1/2 z minus 3/2 z is minus z. And 1/2 minus 3/2 times 7/13. What is that? This is minus 21/26. This is 13/26. It looks like I get make sure I do my arithmetic correctly. I have x plus 3/2 y plus 1/2 z equals 1/2. Y plus z equals 7/13. So I take minus 3/2 the second equation plus the first. So I eliminate the y. Minus 3/2 plus 1/2 is minus 1. Minus 3/2 times 7/13 plus 1/2 is 13/26 minus 21/26 is minus 8/26 is minus 4/13. So I get this system of equations. And now, what does this tell me? I'm sorry, go ahead. Is there a question?
Yeah. How you got y plus z equals 7/13? Where you got the y?
I added this. I took, sorry, from this equation. Do you see where this equation came from?
I saw it.
Multiply this by minus 2/13. That is, I get y plus z 7/13. Just I'm multiplying this second equation by minus 2/13 to give me a 1 here. It also gives me a 1 here, and it gives me 7/13 here.
Okay.
So now I have this system of equations, and this system of 2 equations and 3 variables has the same solutions as the system I started with. And what does this say? This says that if x, y, z is a solution, then x is minus 4/13 plus z, and y is 7/13 minus z. So that any solution x, y, z will be of the form x is minus 4/13 plus z, y is 7/13 minus z, and z is z. So this is the vector minus 4/13, 7/13, 0, plus z times the vector 1 minus 1, 1. And this is the general solution of this system of 2 equations and 2 unknowns. Every solution is of this form for some z. In particular, if I choose z equals 0, this is one solution of the system, and this is of the inhomogeneous system. And this is a particular system. This is a solution of the corresponding homogeneous system. And you can check if you plug in that this is a solution of the original system of equations, and this is a solution of the homogeneous system. Let's see, just for fun, let's see what Maple would give us. So suppose I want to use Maple to solve this system. So I type solve, oops. solve the following system. I put them in curly brackets. 2 times x plus 3 times y plus z equals 1. 5 times x plus y minus 4 times z equals minus 1. Those are my 2 equations, which I put in curly brackets. A little bigger so it's easier to see perhaps. Comma, and then in curly brackets, the 3 variables I'm solving for, right parenthesis, semicolon. So this says, so this gives me a solution in a different form. That x is, if you have y equals 0, you still get the solution. If you have y equals 0, you get different. So this is just another form of the solution. This is if we had solved for y instead of solving for z. In any case, this is Maple's form of the solution of this equation. So Gaussian elimination is something that you learn by doing. So this sort of a general strategy for Gaussian elimination is the following. You have your system of equations. Now, I mean, it could be your system of equations looks like this. Maybe 2x2 minus 7x3 equals 1. 5x1 plus x2 plus x3 equals, I don't know, 5. And 2x1 minus x3 equals 11. So this is your system of equations. And you look to see which is the first variable that occurs somewhere with a non-zero coefficient. Well, it's it's x1. But that x1 with a non-zero coefficient doesn't occur in the first row. So what you might do is like interchange these rows or interchange these equations. So the system now looks like 5x1 plus x2 plus x3 equals 5. 2x2 minus 7x3 equals 1. 2x1 minus x3 equals 11. So all I did to get from this system to this system is interchange equations 1 and 2. And I like doing that because I want to eliminate x1 from all the equations except the first. I could just multiply this equation by a fifth, or that is divide this equation by 5, subtract the multiple of this from the third row, and I eliminate x1. And then I only have to consider the remaining variables. And once I've eliminated x1, then I try to eliminate x2, and I keep eliminating variables until I can't do it anymore. And then I will be able to find the explicit solution of my system of equations. But the only way really that I know to understand what's going on is to study the examples in the book, of which there are quite a few, and do the carefully so you understand every step, and then spend a lot of time working on the homework problems. And if you have downloaded Maple and know the little bit that you need to know to use it, if you don't know it, you can look at some of my lectures online or ask me in a problem session. You can check your work with Maple. Okay. Now, in a couple of weeks, we'll learn a more efficient system to use Gaussian elimination using matrices. But there are one or two other topics I want to discuss first before we get to matrices. But solving a system of equations from Gaussian elimination, if you learned how to solve two equations and two unknowns in high school or in pre-calculus or somewhere along the way, I mean, somewhere along the way you must have, or you wouldn't have gotten to calculus. You're doing nothing different when we're solving a large system of equations in many variables. You are eliminating variables to simplify the system until you can just write down the solution. Okay. Any questions about this? So I haven't really proved any theorems about systems of equations, but now I'm going to prove one, which is a fundamental result. It's very important. It's not very hard, but it is fundamental. And this says something about how you know that a system of equations that's homogeneous has a solution other than the trivial solution when you set all the variables equal to 0. That is the question before us. And so we have a homogeneous system. A11 x1 to A1 n xn equals 0, now to AM1 x1 to AMN xn equals 0. This is a homogeneous system of m equations in n variables. And there is always the trivial solution. The trivial solution is the vector where every coordinate is 0. Because if you let every xi equal 0, then of course you get 0 on the right-hand side equal to 0 on the left-hand side. So a homogeneous system of equations always has a trivial solution. And an interesting question is, when might it have a non-trivial solution? And the theorem says the following: if n is bigger than m, that means more variables than equations, then the system always has a non-trivial solution. A solution that's not all zeros. Okay. And the way we're going to prove this will be by induction on n, the number of variables. Sorry, induction on m, the number of equations. So what does that mean? Suppose m is 1. That means we only have one equation. A11 x1 plus A12 x2 up to A1n xn. And our hypothesis is equals 0, that the number of variables n is bigger than m, which is 1. So if n is bigger than 1, that's the same as saying n is at least 2. So we have one equation in 2 or more variables. And I claim there's a non-trivial solution. So there are two cases. Case 1, A11, this coefficient could be 0. That is, our equation could be 0 times x1 plus A12 x2 plus A1n xn equals 0. Any of these coefficients could be 0. And in this case, if I let x1 equal 1 and all the other x's be equal to 0, we have a solution because we have 0 times 1, which is 0, plus 0 plus 0 plus 0 is 0. So 1, 0, this vector is a solution. And it's not the 0 solution because the first coordinate is different from 0. So that's the case when A11 is equal to 0. That's kind of simple. But what about the case when A11 is not 0? Well, that's almost as simple. We have the equation A11 x1 plus A12 x2 up to A1n xn equals 0. Suppose I let all the x's except the first be equal to 1. And if I solve this equation for x1, I would get A11 x1 minus A12 x2 minus A1n xn. And if I divide by A11, which I can do because this is the case when A11 is not 0, this says that x1 is equal to this. So if I let x2 up to xn equal 1, and I define x1 by this equation, I get a solution. And it's not all 0 because n is at least 2, and x2 and all the other variables equals 1. So if I have just one equation in 2 or more variables, there's a non-trivial solution. Let's look at the next bit. So this is a mathematical argument. This is something that you need to learn to follow. What's about the case m equals 2? So if there are two equations, then the number of variables is bigger than 2, so n is at least 3. So we have two equations in our system, A11 x1 to A1n xn equals 0. A21 x1 to A2n xn also equals 0. So I need to show that this system has a non-trivial solution, a non-zero solution. So there are a couple of sort of simple cases here. So in the first case, suppose A11 and A21 are both equal to 0. In that case, I can let x1 equal 1. And all the other variables, xi to be 0, for I going from 2 up to n. Then I have a bunch of zeros plus 0 times 1, which is 0. This is a solution. So if A11 and A21 are both 0, there's no problem. In case 2, A11 is different from 0, or A21 is different from 0. That is, at least one of these two is different from 0. If A11 is different from 0, good. If A11 is 0, A21 is 0, is non-zero, so I can interchange the equation. So we can assume that A11, this is different from 0. So if this coefficient is different from 0, by subtracting a suitable multiple of the first equation from the second, I can transform this equation, this system, as follows: A11x1, A12x2, up to A1n xn is 0. And if I subtract the suitable multiple of the first equation from the second, I eliminate x1, and the second equation starts with this variable x2. And for this A22 prime x2 up to A2n prime xn equals 0. So I have this system with the x1 eliminated from the second equation equivalent to the first. But if I look at just this second equation, this is an equation in n minus 1 variables, and n is at least 3 in this case. So n minus 1 is at least 2 variables. I have one equation in at least 2 variables. So this equation has a non-zero solution, x2 down to xn. I can find scalars x2 up to xn, not all 0, that solve that equation. But if I take those scalars and plug them into the first equation, I can, A11 is different from 0, so I can solve for x1. I can find x1 that makes this equation 0. So I'm done. So if I have 2 equations and 3 or more variables, the system has a non-trivial solution, non-zero solution. So let's consider now the general case. Suppose the number of equations m is at least 3, and n is bigger than m. So assume we've already proved the theorem. So suppose the theorem is true for smaller m. Suppose the theorem is true for m minus 1 equations in n minus 1 variables. And again, n bigger than m means that n minus 1 is bigger than m minus 1. So assume if I have m minus 1 equations and n minus 1 variables, there's a non-zero solution. And now I'm considering m equations in n variables. That is A11x1, A12x2, up to A1 and xn equals 0. A21x1, A22x2, up to A2n xn equals 0, down to AM1x1, AM2x2, up to AMN xn equals 0. This is m equations and n variables. And again, we have the same 2 cases. Look at the coefficients of x1 in all of those equations. So if all of those is 0, if ai1 equals 0, if ai1 is 0, Jesus. AI1 is 0 for all I going from 1 up to m. Then we just let x1 equal 1 and xj be equal to 0 for all the variables from 2 up to n. So all these variables are 0, everything here is 0. If all of these first coefficients are 0, multiplying by 1 still gives 0, we get 1, 0, 0, 0, 0, 0. That's a non-zero solution of the system. So if all of these are 0, we have a non-zero solution. If AI1 is different from 0 for some I, we can interchange equations so that, in fact, this very first coefficient, A11, is different from 0. If A11 is different from 0, subtracting suitable multiples of the first equation from all the other equations eliminates x1 from the system of equations. So Gaussian elimination gives a system that looks like this: A11 x1, A12 x2, up to A1n xn equals 0. But in all the other equations, there's no x1. It will start with A22 prime x2 up to A2n prime xn equals 0, down to A m2 x2 up to A mn xn equals 0. Now, if you look at that system, again, we have m equations and n unknowns. But if you look at all but the first equation, here we have m minus 1 equations, n minus 1 variables, homogeneous. So there is a non-zero solution, x2 down to xn, for this mini system of equations. M minus 1 equations in n minus 1 variables. But then you take those variables, you plug it into the first equation. A11 is non-zero, so you can find an x1, which gives you a solution of this equation, and we're done. Because now we have a non-zero solution of this system, which is a non-zero solution of the original system. So that is the proof of this basic theorem. For a homogeneous system, if you have more equations than variables, for a homogeneous system, if you have more variables than equations, you have 2 variables for 1 equation, or 3 variables for 2 equations, or 100 variables for 76 equations. There's always at least one non-zero solution. And this is a very powerful theorem, and it will lead us into a new subject, which is vectors and vector spaces and linear independence and the dimension of a subspace of a vector space. And I think that's a big chunk to start, and I'm going to wait until Wednesday to do that. Any questions about this? Again, I remind you, I have an office hour at 7 this evening. You're all welcome to join in. If you have questions and you can't make an office hour, you are always encouraged to send me an email, and we can try and work out a time that works for both of us. But I expect to have office hours, not just today, but a couple more times this week. So either at the beginning or during a class, you can always, at the beginning of a class, is the best time to ask questions about previous lectures or homework problems, or in one of the office hours. Any questions about any of this? Any questions about the homework? Okay. All right, then I think we are done for the morning. back at 11 o'clock on Wednesday. Okay. Be well. Bye-bye.
Thank you.
Thank you, Professor.